Hello everyone and welcome back. In the previous video, we looked at why 5G NR is more energy efficient by design. We discussed lean carrier design, longer sleep opportunities, bandwidth parts, carrier aggregation, UE-DRX, massive MIMO, beamforming, and hardware evolution. Those features give 5G NR a strong foundation for energy efficiency. In this video, we move to the next step, 5G Advanced Release 18 Network Energy Saving. The important change in Release 18 is that energy saving becomes more explicit, more standardized, and more focused on the RAN. Instead of just saying that 5G NR has a flexible design, Release 18 introduces specific mechanisms that help the G node B sleep more, transmit more efficiently, reduce unnecessary radioactivity, and adapt to traffic and QoS requirements. So in this video, we will look at the Release 18 Network Energy Saving Toolbox, including SSB-less SCells, cell DTX and DRX enhancements, CSI enhancements, antenna adaptation, PDSCH power adaptation, joint antenna and power adaptation, conditional handover enhancements, legacy UE handling, and the role of control KPIs and AI or ML assistance. Before looking at the features, let us start with why Release 18 network energy saving was needed. 5G NR already includes several energy efficient design principles. It has leaner signaling than LTE, flexible bandwidth use, DRX, carrier management, and support for advanced antenna techniques. But real networks are not perfectly energy proportional. Ideally, when traffic load is low, base station power consumption should fall sharply. In reality, a large part of the G node B's power consumption can remain relatively static. Even when the cell is lightly loaded, many components may still remain active. That creates an energy saving gap. This gap is especially important during low and medium load periods. The network is still available and ready to serve users, but it may not need all radio resources to remain fully active. Operators therefore need more explicit and granular ways to reduce G node B energy use without harming performance. Energy saving cannot come at the cost of coverage, capacity, latency, reliability, or user experience. Release 18 targets this problem by introducing features that allow the G node B to sleep more, transmit more efficiently, and adapt dynamically to traffic and QoS needs. The Release 18 Network Energy Saving Toolbox can be grouped into two broad areas. The first area is about creating more cell sleep opportunities. This includes SSB-less SCell operation, cell DTX and DRX enhancements, and faster handover away from cells entering an energy saving mode. The second area is about transmitting more efficiently. This includes CSI enhancements, antenna adaptation, PDSCH power adaptation, and joint antenna and power adaptation. The sleep more side is about reducing unnecessary activity when resources are not needed. The transmit more efficiently side is about using the right amount of antenna and power resources when transmission is required. This distinction is useful because not every situation allows the cell to sleep completely. Sometimes the best option is to turn off or reduce activity. Sometimes the best option is to continue transmitting, but with fewer antenna resources or lower power. The Release 18 toolbox gives the network more options, so it can choose the right energy saving method for the right situation. Let us start with SSB-less SCell operation. In carrier aggregation, a secondary cell is often used mainly as a capacity booster. The primary cell provides the main coverage and mobility anchor, while the secondary cell adds extra capacity when needed. The energy issue is that a secondary cell may still need to transmit periodic synchronization signal blocks or SSBs even when it is not carrying much traffic. Those SSB transmissions consume energy. Release 18 extends the ability to use SSB-less secondary cells in certain scenarios, including interband FR1 co-located carrier aggregation cases. The idea is simple. If the SCell is mainly used as a capacity layer and the UE can rely on the primary cell for essential synchronization and coverage support, then the SCell may not need to transmit its own SSBs in the same way. By omitting SSB transmission on the SCell where applicable, the network can reduce the energy overhead of the secondary cell. The SCell can still provide capacity through downlink and uplink channels, but without the same cost of periodic SSB transmission. So the key message is use the secondary cell when extra capacity is needed, but reduce its always on signaling burden when possible. Next, let us look at cell DTX and DRX enhancements. Cell DTX means the G node B can reduce or stop transmissions during periods of low or no user activity. Cell DRX creates predictable active and inactive periods for the cell. The challenge is coordination. If the G node B sleeps at the wrong time, the UE may expect signals or channels that are not available. That can affect connectivity, scheduling, mobility, or user experience. Release 18 improves the coordination between cell level DTX or DRX and UE connected mode DRX. This allows the network to align UE wake-up periods with G node B active periods. During active periods, the UE and G node B can communicate normally. During sleep periods, the UE should not expect certain signals or channels on the corresponding cell. This helps create longer and more useful G node B sleep windows. The goal is not just to turn off transmissions randomly. The goal is to create predictable and coordinated active and inactive periods, so the G node B can reduce energy consumption while connected UEs are still handled correctly. Better alignment means longer sleep opportunities, lower G node B energy use, and protected user experience. CSI stands for Channel State Information. Normally, CSI helps the network understand the radio channel and choose suitable transmission parameters. In Release 18, CSI reporting is also enhanced to support energy saving decisions. The UE can provide CSI sub-reports for different transmission options. For example, one report may correspond to full transmission, where all antennas are active and normal power is used. Another report may correspond to reduced antenna resources. Another may correspond to reduced downlink power. Another may correspond to a specific transmission shutdown pattern. This helps the G node B compare different energy saving choices before applying them. The G node B can then choose an adaptation that balances energy saving with the required user performance. This is important because energy saving decisions should not be blind. If the G node B reduces antennas or power without understanding the likely impact, user throughput, coverage, or reliability may suffer. CSI enhancements give the G node B better information, especially in the spatial and power domains. The key message is that better feedback enables smarter energy saving choices. Antenna adaptation is one of the important Release 18 techniques for reducing radio energy use. Massive MIMO uses many antenna elements and RF chains to provide high capacity, beamforming gain, and better spectral efficiency. But full massive MIMO capability is not always required. During low or medium load, the cell may not need all active antenna resources. In that case, the G node B can reduce the number of active transmit and receive antenna elements. For example, a higher load situation may use a 64T configuration, while a lower load situation may use a reduced 32T configuration. This can reduce RF chain and radio unit energy consumption. However, there is a trade-off. If too many antenna resources are switched off, the network may lose beamforming gain. Capacity may fall, user throughput may be affected, cell edge users may be more sensitive to the change. So antenna adaptation must be controlled carefully. The network needs to monitor KPIs such as beamforming gain, user throughput, coverage, latency, drop rate, and QoS impact. The key message is that antenna adaptation can save energy in the RF chains and radio unit, but KPI monitoring is essential to avoid harming user performance. PDSCH stands for Physical Downlink Shared Channel. This is the main downlink data channel used to carry user data. PDSCH power adaptation reduces the transmission power used for the downlink shared channel when full transmit power is not required. This is a power domain adaptation. Instead of always transmitting at a high power level, the G node B aims to deliver the required user performance with less power. For example, if the UE has good radio conditions or if the data rate requirement is moderate, the network may not need to use full PDSCH power. Reducing the power can lower transmission energy while still maintaining the required throughput and user experience. But again, this has to be controlled carefully. If the power is reduced too much, throughput may fall, retransmissions may increase, latency may rise, or coverage may be affected. So the aim is not simply to reduce power, the aim is to right size the power. Use enough power to deliver the required service but avoid wasting energy with unnecessary transmission power. PDSCH power adaptation cuts transmission energy while aiming to preserve required user performance. The strongest practical story is not antenna adaptation alone or power adaptation alone. It is the combination. Antenna adaptation works in the spatial domain. It changes how many antenna resources are active. Power adaptation works in the power domain. It changes how much downlink power is used. When these two are used together, the network has a richer set of choices. For example, it may reduce power slightly while keeping antenna resources active, or it may reduce the number of active antennas while maintaining enough power, or it may use a combined setting that gives a better trade-off between energy saving and user experience. Nokia's analysis suggests that power and antenna adaptations can provide a strong practical trade-off between energy saving gain and throughput impact, especially around daily average load. But the gains from multiple techniques are not simply additive. If two techniques affect overlapping parts of the radio chain, combining them does not always give the sum of individual savings. That is why careful optimization is essential. The goal is to find the best balance between network energy saving gain with controlled impact on user perceived throughput. Joint antenna and power adaptation often provides the most practical balance between energy saving and user performance. Now, let us look at mobility. If a source cell is about to enter an energy saving mode, users may need to be moved quickly to another cell. This is where conditional handover becomes important. Conditional handover allows handover conditions and target cell information to be prepared in advance. Then, when the condition is met, the UE can execute the handover more quickly. Release 18 introduced enhancements to support NES cells in this context. The idea is that if a source cell is entering NES mode, the UE can be handed over to a neighboring active cell before the source cell reduces activity or goes to sleep. This helps maintain service continuity. The source cell can save energy, but users are not left stranded on a cell that is becoming less available. In practice, this helps protect user experience while allowing more aggressive energy saving behavior. The key message is that energy saving and mobility have to be coordinated. A cell should not simply go to sleep if connected users still depend on it. Conditional handover enhancements help move UEs faster, so NES cells can save energy without disrupting users. Release 18 also has to consider device compatibility. Not all UEs understand the new energy saving behavior. A legacy UE may not understand cell DTX or DRX behavior used by a Release 18 NES enabled cell. If the UE camps on the cell, it may expect signals or channels that are not transmitted during energy saving periods. That could create service problems. To avoid this, Release 18 introduced a new optional bearing bit in SIB1. SIB1 is System Information Block 1. It provides important cell access information to UEs. With the optional bearing bit, the network can restrict access so that only UEs capable of supporting the relevant cell DTX or DRX behavior can access that cell. Legacy UEs can be redirected or barred from camping on the NES enabled cell. This is simple but important safeguard. It helps operators deploy more advanced energy saving techniques without accidentally creating problems for devices that do not support them. The key message is that energy saving must work across the real device ecosystem, not only in ideal Release 18 scenarios. Network energy saving is not just a set of radio features, it is also a control problem. The G node B has to decide when to sleep, when to reduce antennas, when to reduce power, and when to reactivate resources. Those decisions should be based on data. Useful inputs include UE feedback, network KPIs, cell load, UE locations, traffic characteristics, and QoS targets. For example, the network may consider CQI, RSRP, throughput, mobility, PRB utilization, BLER, latency, active UE count, traffic volume, and service requirements. AI and machine learning can help by predicting what is likely to happen next. They can help predict future cell load, UE mobility patterns, and energy saving opportunities. This allows the network to make better decisions about when to apply energy saving actions. The control output could be cell sleep, antenna adaptation, PDSCH power adaptation, or reactivation. The important point is that AI or ML should assist the decision-making process, not replace the need for KPIs and engineering guardrails. Energy saving should be optimized while maintaining coverage, user experience, and performance. There is no single best network energy saving technique for every network. The right feature depends on the real deployment. A low load cell at night may be a good candidate for SSB-less SCell, cell DTX, antenna adaptation, or power adaptation. A medium load cell may require a more careful balance. Some techniques may still be useful, but timers, thresholds, and KPI guardrails become more important. During busy hour, the priority is usually performance. Aggressive sleep may not be appropriate. Some power adaptation may still be possible, but coverage capacity and user experience must come first. The most suitable technique depends on several factors. These include actual cell load, UE distribution, traffic type, QoS targets, device support, and the deployed RAN hardware and software. For example, if the hardware cannot switch off certain RF chains efficiently, antenna adaptation may not deliver the expected savings. If many UEs do not support the required Release 18 behavior, some features may have limited applicability. If the cell has a difficult coverage footprint, aggressive sleep or power reduction may create problems. So the operational message is simple. Save energy, but not at the cost of unacceptable throughput, coverage, latency, or reliability impact. Use the right NES techniques at the right time with the right parameters for your network. That brings us to the end of video 4. In this episode, we looked at 5G Advanced Release 18 Network Energy Saving. Release 18 takes the 5G NR foundation and adds more explicit energy saving capabilities for the RAN. We covered SSB-less SCells, cell DTX and DRX enhancements, CSI enhancements, antenna adaptation, PDSCH power adaptation, joint antenna and power adaptation, conditional handover for NES cells, legacy UE handling, and the role of control KPIs and AI or ML assistance. The main point is that Release 18 mainly focuses on connected UEs, user-specific signals and channels, and smarter control of G node B transmission behavior. But the energy saving story continues in Release 19. In the next video, we will look at how Release 19 expands the scope further. This includes on-demand SSB operation for SCells, on-demand SIB1 for idle and inactive UEs, adaptation of common signal and channel transmissions, PRACH and paging adaptation, low power wake-up signal and wake-up receiver concepts, and energy efficiency as a service criterion. So video 5 will move from Release 18's connected UE and user-specific focus towards wider system-level energy-saving enhancements. Thank you for watching. If you found this video useful, please like the video, subscribe to the channel, and check the links in the description for additional resources. We hope to see you again soon in video 5. Goodbye.